remove default video. Okay, what we got here? Yeah, that's what we are interested in. I have created an application. Take a look. Something familiar, isn't it? What we saw in our previous lecture. Case 1 omega t, ideal sign. We saw it. I can add 1/3 of the third harmonics. 1/3. And we see something close to rectangular. This one, clear original, this one. That's what my machine gave us. Yes? Have you seen this? It's closer, isn't it? Now I would like to do what? I will add 10 harmonics. It's like here I have first, second, third, so 7 position. If I had not 7 but 10, it will look like this. See, it's closer, yeah? You see, if I add more components, it became closer, isn't it? 100. But this, you see, something refused to disappear. 200. Machine. Oops. See what's going on? See this needle? Do not disappear. And I can't remember what's the maximum. 300. Yeah, 300. Needles do not. Can you see it? It's small. And it will never, for example, like this, 25. It's an interesting problem. The short needle never disappears. It's a result of precision or quality factor selected by Fourier. Fourier used Euclid norm or difference energy. Energy of this needle goes which way? To 0. So energy will be 0, but amplitude not 0. It's a forgive me, peccatum original or Fourier law. The problem is what this signal, when it goes up, what's the rate of change, first derivative, when it goes up? We have an ideal rectangular signal. When here it should go up. When it goes up, what is the rate of change? Infinity. And when it goes down, rate of change is minus infinity. But sine and cosine, what's the first derivative of cosine? Sine. First derivative of sine is cosine. They are limited. Idea, when we, what's the value of signal of this fat line here at 180 degrees? If we approach from this direction, it's 10. If we approach from this direction, minus 10. But what's the difference? What's the value of Fourier law? 0. This signal is like. Maybe I switch to here. You can do something like this. 1. Some resistance. 8. put a battery of 10 volts here and rotate it. Wait 1 second, where is my phone? This generator, for example. Here, you see? It's a way to get direct current from alternating. See these commutation rings? It's fun. Here they are. Put a battery here, and you will have plus 10, minus 10, plus 10, minus 10. They should be equal. 0, 180, 360 degrees. You have a break at the moment when from this contact shifts, it rotates. At the moment when switched, we have a break. So this line is interrupted, but Fourier rule is uninterrupted. It's continuous. And this one has interruption. At the moment surface is changed. It was expected, problem was expected. At the moment when Fourier developed, think Lagrange, here of French Academy of Science, instantly pointed this problem. But at the moment when fast changing function goes up, your rho will fail. That's what Lagrange expected, and there was a quite heavy battle between Lagrange and Fourier. Problem was expected, problem was observed, but very for quite a long period it wasn't, let's say, researched well until 1885. Gibbs investigated it, and now this problem has a name of Gibbs paradox. Let's say recoil from fact what? For Fourier selected, Jean-Baptiste Fourier selected Euclid norm as a quality criterion. We substitute with an uninterruptible function something what has interrupted. Okay, maybe. Let it be visible what I'm willing to write. Here is idea as Gibbs presented it. Let's say A, B, we have some y being function of x, k is x, and at the point A we have limit of function A as epsilon when epsilon is tending to 0, A and A plus epsilon B and epsilon into 0. We have something like this, function with interrupt. Fourier rule will make some will show us some strange behavior at the breakpoint. What was idea of Gibbs? Gibbs offered to investigate one specific function. Can you guess its name? Gibbs function. Yeah, Gibbs function equals to minus 1, 0, sorry, x 0 and 1, 0. Something familiar? Familiar? It's our rectangular function with E1 but drawn not from time but from it will be equals to omega t. Drawn in radians. Here what we'll see. Do we know Fourier representation for this function? We know? We just saw it. Gibbs function as any obscene rectangular function can be substituted with 4 divided by p sine x plus 1/3 sine 3x plus 1/5 sine 5x plus blah 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 plus it will be double swan x divided by minus 1. Here it is. We saw it. Yeah? Familiar function. Now question. First, why this function? It's an ultima. This function has the highest changing rate or rate of change from all possible functions. If we can estimate a row error for this function, it will be the upper limit for all errors. That's why how to investigate. We need to analyze something known as Sm from x. It's a sum of n first n elements. It will be 4 divided by p. Sum by I changes from 1 to sine of double I minus 1 x divided 1. Yeah. Here on the screen, what do we see? This line is Sm for n equals 25. What is written on the table is a blue line, and here is the n number. Okay? So idea is to perform an investigation on this function. How do we investigate function or make research on them? What should we get? Extrema points, yeah? And how we will get extrema points? Yeah, we need derivative. So we need to analyze yes. Actually, we need to solve an equation to get extrema points. We will need to solve equals to 0. Get roots of this equation, and these roots will point us an extrema points. Yeah? Have you heard it on math classes? Yes. How can we do it? Problem. What we need to solve something, no, it will be 4p cosine x plus cosine 3x plus cosine 5x and so on equals to 0. We will need to solve, this is not important, we will need to solve equation sum of cosines equal to 0. Any idea how to solve such equation? What Google say? How to solve sum of cosines? Yeah, but they don't cancel each other. That's why it's a Gibbs paradox, not Dolgitzer's paradox. Gibbs knew very well complex math. And Gibbs find one idea in the area of complex rows. There is a progression. A power all multiplied. A power 1 plus a power beta plus a power double beta plus a power triple beta and so on. A power, wait 1 second, they are complex. They all are complex minus 1 beta. Such complex progression, sum for this progression is known. It will be a power of multiplied by 1 a power dot m beta divided by 1 minus a power dot beta. Of course you will ask, where's the link between sum of cosines and this complex progression? It's not clear. Maybe for you not clear, but for Gibbs it's clear. It was clear. Why? Because Gibbs understood what with Euler formula, it's possible to take real part from this progression. Real part from this will give us real part from this sum will give us cosine alpha plus cosine alpha plus beta plus cosine alpha plus double beta and so on plus cosine of alpha plus m minus 1 beta. This is a real part of this progression of power. And this real part equals to cosine alpha plus 1 beta divided by 2 sine m beta divided by sine of beta divided by half. Nice formula, isn't it? This formula converts sum of cosines into multiplication. So, assume what beta equals to double x and alpha to x. Who and why? Yakov. Accounting costs. Killing me. Cosine. Cosine. Accounting costs. Killing me. Now, what we will get? Now we can write cosine plus cosine triple x plus cosine 5x plus cosine double minus 1x equals to cosine and x sine and x divided by sine x. Yeah! Which is equal to sine double and x divided by sine x. Yeah. Good to know complex mass sometimes, isn't it? Problem just solved. First, we can make some, let's say, interim conclusion. Can be represented as 0x as an integral of some interim time function. But the most idea, we need extrema points. Extrema points, this gives us extrema points. We just need to solve sine double and x equals to 0. We will get extrema points actually from 0 to p by half, but it's not it's not important because we need a maximum one. We need to set, let's say, ceiling for the error. Actually, if we know this point, this one, we knew the worst case, and it will solve us for us everything. So extrema points will be located at KT divided by double M, where how it will work. This extrema, this K1 is the highest, the first one. This one corresponds to K1. Now, what we need? Difference. How big is this difference? Or let's say ceiling for the error. Error will be no bigger than this line, because this one is the first one is highest. It marks maximum possible difference. It's clear. Okay, let's take the first one. For the first one, what we need? This might we will have something like this. 2 divided by P, we need to integrate from P to N sine of NT divided by sine P dt. Now we need a substitution. Y will be double N time to get something familiar from the P sine of Y divided by double N sine Y divided by double N dy. We will make a substitution. Looks nice, but still not solvable. But what do we know? Sine of x when x tends to 0 approximately equals to x. Yes? Sine of small angles approximately equals to angle. So, when we have row long enough, tending element number to infinity, also meaning what it's going towards 0. Take a look. You see where the extrema is now. See? I'll switch, I will double. Well, I will quadruple. 100. See where extrema shifted? The longer row, the closer this extrema point will be to this switch point. Okay. And this, okay, I want 10. This one for 10. So it shifts forward. Longer row meaning the x point of extrema shifts towards 0. So, with this, we can approximately replace with the angle itself. y divided by y dy. And this function is tabulated. It's integral signs, and we have for a long time tables of this function. This is known, it's integral sign of p, and it's 1179, and so on. You can find the integral sign in last table. What's the conclusion? Max possible error of this overshot is 18%. Gibbs not only pointed the problem with Fourier law, but approximating with uninterruptible function interrupted original, we will see oscillation. Gibbs also found what difference this overshot in amplitude never exceeds 18%. But problem persists. When you model with the Fourier law function with the sharp changes, for example, some 5 years ago, modeling electrical machine, it has grooves with a quite sharp cutting. So very strange oscillations. Why? Because of Gibbs paradox. When changes are sharp, Fourier law will oscillate around original function with maximum difference in amplitude 18%. Okay, now we can go forward. Can we go forward and take something? What's good in Fourier law? Why we are taking time speaking about Fourier law? Fourier law gives us ability to replace any periodic current with a set of 1 DC and multiple ideal IC currents. Voltage or current. Good? Good, because we all knew electrotechnics theory, and we are all able to solve Kirchhoff equation. Yes? Do you know Kirchhoff equation? What Facebook says about Kirchhoff equation? What a disaster. Why are you wasting your time? Can we use nodal potential technique? Do you know about nodal potentials? Huh? Really? Strange. No. When we calculate a potential, we will have potential diagram. No, idea of first Kirchhoff. Idea of first Kirchhoff law. We select one node as a base, and we have current from all nodes as a difference of potentials. And we will get nodal admittance matrix. When we sum all admittance, so it will be admittance between nodes multiplied by difference of potential. As a result, we will get a nodal admittance matrix and a system of linear iteration, potentials of all nodes. Then with the help of Ohm law, it must be nodal admittance matrix. One second. if needed. My God, what a beauty. I have this site, Dolgitzers at the effort. And here I have computer application and power engineering. And you can find a lecture, solution of DC network, of AC network in two parts. And here, for example, for AC network, over Hazy site and Charles Pratel Steinmetz. And here all technique, step by step, how you can solve a network. What's good? So, block. You will end with, wait 1 second, case nodal potential system of equations. Okay, it's different course. If you need, very simple. It's computer application and power engineering, if needed. Yeah, it's for, Adaptronics program don't have this course. But if you need, all lectures are available. Okay, what I'm willing to say. We have, let's say, tools for direct current and ideal AC current, alternating current. But for rectangular current, we have nothing. With the help of Fourier law, we can substitute one complex periodic voltage or current with a set of ideal components, one DC and multiple RC components. Electrotechnics theory gives us all the tools needed to solve such network as we want. At the end, it will end. At the end, we will get a system of linear equation easily solvable. But what about non-periodic signals or aperiodic signals? What about signals which do not repeat? This idea of original idea of Fourier law works for a repeating signal. But what about signals which do not repeat? Can we get the same transform for non-repeating signal? It's a question. Okay, I think I'll to make it all in order, I will start another stream. I will start another stream. It's